I was able to, in a joint paper with a former PhD students, I was able to introduce a notation for a representation for partitions as two-line matrices. And later we realized that by using those two-line matrices, it was possible to draw a lattice path from the origin to the line x plus y equals n for each integer n. And then in a few months ago, a PhD student was able to find a new relationship, a new recurrence relation for the partition function using those lattice paths. And so if you are able to represent partitions as a lattice path, it seems to me that this can be important, okay? Because he was able to find, as I just mentioned, a new recurrence relation for the partition function, which is quite important. And so in this paper, at the end, we will have lattice paths. And so that's the reason why I mentioned the results we have here, okay? And so actually we will see that we have here a new formula for Fibonacci sequence. We have an interpretation for Fibonacci using partitions. And at the end, as I said, we have a representation using lattice paths, okay? So here we have them in those two papers by Lucy Slater. She gave a list of 130 identities, all of them of the larger Ramanujan type. Later, Andrews introduced a two-variable function, and he was interested in the combinatorial interpretations for those identities. In my thesis, more than 30 years ago, I was able to give explicit conjectures for families of polynomial that can be obtained by using the Andrews method, okay? And from the 130 identities, I was able to find families, explicit formulas, conjecture, okay, for explicit formulas for just 74 identities of that list, from that list. I couldn't do for all because I didn't have, at that time, we didn't have computers like programs like Maple, for instance, to help in finding those for all of them, okay? And so in this paper, we are going to prove the conjectures. In my thesis, I gave the conjecture for explicit formulas, and then I was able to prove just a few of them, because as you will see in a moment, it takes quite a long time to do the calculations. Many years later, a friend of mine, Andrew Seals, he wrote a program to do the calculations. And so the conjectures that I have found at that time, they are all correct, okay? And so we'll see results like this one in the following. Like, for instance, we have the following. That's this is the polynomial family related to the identity number 9 and 4. Okay, 9 and 4. This is, and we prove in this paper that this sequence here is actually the generating function for partitions. Look into at most any parts in which every even is smaller than the largest appears at least once. Okay, and the family related to the number 9 and 9 is the generating function for partitions into at most any parts in which the largest part is even and every even is smaller than the largest appears at least once. Okay, the Fibonacci is this sequence. We will see that from what we will be done, we can get a new formula for the Fibonacci number and also a combinatorial interpretation in terms of partitions. Okay, this is a standard notation. Here we have a few important properties for the Gaussian polynomial. Okay, the Gaussian polynomial is a generalization of the binomial numbers. Okay, and let's see the first family of polynomials. And so this is the function following Andrews related to identity number 904. Okay, and then from here we have this relation, and now in order to find the occurrence relation from this is a functional equation, we have the following substitution. And just calculation, elementary calculations, in order to get this recurrence relation. Okay, and as I said, this is one in my list that I was able at that time to find an explicit formula. This is a conjecture. Over here, we have proved that this is in fact true. Okay, as you can see, I will not go into details, a lot of calculations in order to prove that this is the explicit formula for those polynomials. Okay, so a lot of calculations. At that time, we didn't have by hand. The maple was, I was using at that time the scratch pad, the name of the program that people at MIT was writing. Okay. Now, okay, então completely we have finished the proof that is in fact the explicit formula. Okay. Next, we make a few observations regarding the combinatorics of those polynomials. And knowing that this is the coefficient of this power of t in this expansion, then we can see that the coefficients of this guy in this term is just the generating function for partitions into exactly any parts in which every even is smaller than the largest appears at least once. Because we have this factor in the denominator, it's here, then actually we have the following results, the following theorem, that this family of polynomial is the generating function for partitions into at most any parts in which every even is smaller than the largest appears at least once. Okay? But now look, we know that P0 of 1 is 1, this guy is 3, and this 1 is equal to that. And that, for the Fibonacci sequence, we have F2 equals 1, 4 is 3, and we know this. And so now we have that Cn of 1 is Pn of 1, which is the Fibonacci in position 2n plus 2. Okay, and so we have proved the following. Now that the total number of partitions into at most n parts, in which every even is smaller than the largest, appears at least once, is given by this number. But what happens, and this is quite interesting, okay, that polynomial at q equals minus 1, we can get this. This is equal to that. And so, which tell us that for q equals minus 1, we have all the Fibonacci numbers. Okay. Now we have an illustration which is quite nice. In order to be able to see what happens combinatorially at minus 1, we have to observe that when change in 2.1 q by minus q, the only term that changes is this one. And that now the coefficients is going to be just the number of partitions, as described in that theorem, having an even number of odd parts minus the number of those with an odd number of odd parts. Let's look at this table and then we'll see what's going on. Okay, let's take 2. Okay, I have here the total number of partitions, okay, of 2 for n equals 2 into at most 2 parts in which every even less than or equal to the largest part appears at least once. Okay, every even appears at least once. And over here, I have those in which the every even appears at least once, but the number of odd parts is even. And over here, the number of odd parts is odd. If we take the total number over here, we have this, which is f in position 2n plus 2. If you take this number minus this number over here, have 5 minus 3 is 2, which is Fibonacci in position n plus 1. This is a quite nice interpretation. Okay, this is for 3, and so I have we list here just the table, those 5 columns. Okay, for a few values of m, and this is just an illustration of this theorem. Okay, and so that is what I have just mentioned, that the total number of partitions into at most n parts in which every even is smaller than the largest appear at least once, and having an even number of odd parts minus the number of those with an odd number of odd parts is equal to this guy. Okay, and so this is what I have just mentioned about that table. Okay, which partitions we have in each column. Now, for the second family of polynomials, okay, we have these following the others, and this is the family of polynomials related to identity 9 and 9. Okay, and this is the family, and here is the conjecture that I gave at that time. The proof for this conjecture, it's here. A lot of calculations, amazing. you have to expend a few hours to do this. Okay? Okay, to see that this is an explanation why that this expression is equal to 0 to finish the proof for the explicit form of that family. Okay, now an explanation about the combinatorics. Okay? Now this is the generation for partitions into exactly any parts in which the largest part now is even and every even is smaller than that appears at least once. Okay, because of this factor, we have this theorem that the generation of partitions into at most any parts in which the largest part is even and every even is smaller than the largest appears at least once. This is the at Q equals 1, we have those values. This is the same for Fibonacci. And so we have here, before we have over here the positions. Okay, look at this table. We had, okay, F2n plus 2 in position even index. Now we have the odd ones. Okay. Now we have the odd ones. Okay, over here, look. And then, because of the factor 1 minus t, we have that actually that the total number of partitions at most any parts in which the largest part is even and every even is smaller than that appears at least once is equal to Fibonacci in this position. Okay. Again, for t equals minus 1, we have the difference between those two sets. And the result is now over here. Look, the total number in which the largest part is even and every even is smaller appears at least once. In this column, we have an even number of odds, and over here, an odd number of odd parts. Or let's take this example. Okay, I have 9 plus 4, which is 13. Position 20 plus 1. Okay, and over here I have n plus 2, and so here I have partitions in which every even is smaller than the largest part appears at least once, and the number of odd parts is even. Over here, the number of odd parts is odd. And so this quite interesting combinatorial interpretation for Fibonacci. Now we can get from those formulas, we can get a formula for Fibonacci. We know that the limit as q goes to 1 of the Gaussian polynomial is equal to our binomial coefficients. Okay? And so let's go there in that formula and take the limit. And we will get this. This is the binomial theorem. Don't worry, this is a finite sum, because when this is greater than that, we have 0, of course. And so we have here the formula for Fibonacci. Here I have a formula for even and odd positions. Look over here. Cn of 1 is the Fibonacci position par, even, and over here in position odd. Okay. Those are, we have them. And so far, we have them formulas, explicit formulas for Fibonacci in terms of the binomial coefficients, and also the combinatorial interpretation using partitions for this quite important sequence that we can see many different areas. Okay, the Fibonacci numbers. And now the reason why I have decided to talk about this. And the reason, as I mentioned, I will say this again, that a few months ago, students was able to give a new recurrence relation for partitions, for unrestricted partitions. And he was able to do that by using a representation for partitions. As I said, I was able to introduce a two-line matrix representation for partitions. And from the two-line matrix, it was possible to draw a lattice path. And that student, he was able to find the recurrence relation for Fibonacci, for the unrestricted partitions by using the lattice path representation. Now we have here in Narayama, lemma 4a. Narayama is this guy over here, lattice path combinatorics with statistical applications, Toronto 76. And he has this formula. This is the total number of lattice paths from the origin to Mn, not touching those two lines. Okay. Now we can look at those two formulas here and this one, and we will see that by comparison, considering that we can write for 1 and for 2, okay? In this way, okay? Now we can have the following, which we can conclude that by comparing these, not here is not 4.4 or 4.5, but 5.2 and 5.3, okay, with this formula, okay. We have actually compared those two with this one, and we got this, okay. And so we have now a nice combinatorial interpretation. We know the combinatorial interpretation for these and these in terms of partitions, but now we have another interpretation in terms of lattice paths. Okay? Now we can conclude that this I equals 1 or 2, okay, is the number of lattice paths from the origin to these points, not touching those two lines, x minus 1, okay, x plus 4 for I equals 1, and the other situation for 2n plus 2, x minus 2, and y equals x minus 2, and y equals x plus 3. Okay? And so we have a very interesting combinatorial interpretation for Fibonacci, okay, in terms of partitions. But now we are dealing with lattice paths, okay. And so, as I said, it was quite nice to know that from the lattice path representation, it was possible to get a result that is not a trivial one, a new recurrent relation for the unrestricted partitions. Of course, that here we have, as I will try together with that student, former students, to use this, hoping to get some results, some different recurrence relation or so. And so those are the, in this paper, okay, this was the, and this paper, okay, this was the thesis, the PhD thesis from this guy, okay, and I would like to thank you for the invitation one more time, and if you have any questions, I will be glad to. But the reason, as I said, was the lattice pass possibility. Okay.
Okay, thank you, Plínio, for this nice talk. Let me start with one question here. When you start doing all these calculations, and at the end, you have this, it seems to me like magic, no? Because it's a very complicated formula, and suddenly you have the Fibonacci numbers. But you are in some way expecting this to happen, or?
No, at that time, what happens is that when we did this, actually this guy, he finished his master degree and also the PhD degree here working with me. He is from Serbia, and then he went to United States to work there. And we got some very interesting results. And I had at that time those conjectures. And as I said, I was able to prove just a few because the work, it's amazing. Later, as I said, Andrew Seals was able to write a program to do all the bad stuff, I mean, the huge calculations. And so over here, when I was dealing with things, it was easy to see that over here, okay, the recurrence relation, okay, was this one. And of course, that we know that this is equal to this. And so it was easy to recognize Fibonacci over here. Okay, and it was really nice when we were dealing with this. I didn't know that we will get Fibonacci. Didn't know. And over here, as I said, we had the Fibonacci index even, and then we have all the, okay, over here with the odd parts, even, and in this column the odd parts being odd, okay, and so, which was nice at that time, at the end, was not only the explicit formula for Fibonacci in terms of over here, okay, with those two formulas for Fibonacci, and also this combinatorial interpretation for in terms of partitions, and that's finally this lattice pass. But at that time, I didn't know that the lattice pass representation could be so important. Okay.
But you know that I'm very impressed with you experts in partitions, how to look at this enormous, gigantic formulas and see interpretations. This always impact me very much. Let's see if there are other questions and comments.
Emar,
Yes.
just a few words. I agree with you. When I see Plínio giving those combinatorial interpretations, I am really excited to try to understand, because they are really amazing. So just this comment.
Other comments or questions? Okay, so let's thank Plínio again. Thank you, Plínio.